I would like to thank UNIMAP and the Centre of Excellence for Frontier Materials Research for inviting me to give this talk. As was already mentioned, I do have an ongoing connection with UNIMAP, and I spent a very pleasant few days there about 8 years ago. And I'm very interested to learn of the development of the centre since then. This talk is really a very unusual one to be the plenary talk for this kind of conference. It really doesn't have very much directly to do with the subject matter of this conference. But over the years, I have been frequently invited to try to give a little advice to young people who are entering the field, in my case, the field of physics research. And I tell them several things, and I'll perhaps come back to this at the end of this lecture. But one of the things I do tell them is don't really worry too much about reading the existing literature on the subject on which you're trying to do research. That sounds a little peculiar at first, and therefore in this talk I would like to explore this theme a little further. I'd like to ask, when is it and is it not a good thing to have read the existing literature on the subject of your research? I would take examples mostly from my own experience, simply, of course, because I am much more familiar with that, but to prevent it being too much exclusively about myself, I will just start off with a couple of examples which are much better known from the history of physics. I imagine most of you are not, in fact, physicists, or certainly not professional theoretical condensed matter physicists, which is what I am, and therefore I didn't think it would make a lot of sense to show you a whole lot of equations. I do have slides of the relevant equations, and if I were giving this talk to a different kind of audience, I would show them, but I imagine that is not going to be particularly interesting to many of you. So this is really meant to be just a sort of fireside chat, and I suggest you just sit back and hopefully enjoy it. Okay, so I'll start off with a couple of examples from the history of physics. The first person I'll just say a little about is Galileo. Now, Galileo was a very prestige and priority conscious person, extremely so. And so I think basically he deliberately tried not to find out what people had already done on the topics that he was interested in. And in particular, when he started thinking about the dynamics of bodies in free fall, and eventually came up with the law, which we now believe to be correct, the law of uniform acceleration in the Earth's gravitational field, he didn't go back, he didn't bother to go back and really find out whether anyone had thought of this before. In fact, they had. There was a group of people, I don't think we even know their names, unfortunately, but there was a group of monks at one of my Oxford colleges, Merton College in Oxford, who in the 14th century had actually worked out a lot of what Galileo worked out later. Now, the fact that Galileo didn't know about this, I suspect, didn't hurt him. In fact, again, I suspect if he had known, it would have made him less interested in trying to develop the subject. We might never have had his marvelous work here. But as I say, he really didn't pay a lot of attention, not just to existing theory, as in that case, but also even to existing experiment. A very famous example is his argument about what would happen if you dropped a stone from the mast of a moving ship. And of course, Galileo concluded that the stone would actually land at the bottom of the mast. Now, one of the other characters in the dialogue in which he says this says, well, have you actually done that experiment? And Galileo says, no, I haven't, but I know how it must come out. And in that particular case, of course, he was right, and his intuition did work. But in some other cases, it really let him down fairly badly. For example, he had a totally sort of cockamamie theory of the tides, which, among other things, predicted you should just get one high tide per day. Now, admittedly, Galileo lived in Italy, and he'd never left Italy in the whole of his life. And sure, the tides in the Mediterranean are not very spectacular. But surely he must have known travellers who had been, for example, to the North Sea and seen that the tides there were certainly not once a day, but twice a day. But he just didn't bother. So this lesson of that is that sometimes not knowing about the experiments can do you no harm, but in other cases it most certainly can. The second example, which I think may be quite interesting, is that of Einstein. Now, of course, when people learn about the history of the theory of relativity, then they usually learn about the Michelson-Morley experiment, the famous experiment in the late 19th century, which showed that you could apparently not detect the motion of the Earth relative to the ether, which was what the existing theory, the so-called ether theory in those days, predicted. Historians of science argue a lot about whether Einstein actually knew about the Michelson-Morley experiment or didn't. But again, I suspect it wouldn't have made an awful lot of difference in his case, because he was really starting from a sort of totally, if you like, a priori notion about space and time. And so in some sense, it had to come out that way. In fact, Einstein, when he wrote his famous paper on the electrodynamics of moving bodies, this was the paper which introduced the theory of relativity in 1905, I think I'm correct in saying that Einstein did not cite a single existing reference. Now, nowadays, I guess you could get away with that, but in fact, he didn't. And this was because I think basically he knew in his heart that all the existing papers, which were based on one variant or other of the ether theory, simply had to be wrong. And of course, again, in this particular case, he was right. So sometimes it works. But let me now go on to some of the episodes in my own career in physics, and which are relevant to this question of how far one should or should not try to familiarize oneself with the existing literature. I'll take these slightly out of order historically. The first one I'll just say a word about is some work I did as a young junior faculty member in physics at the University of Sussex in the late 60s. I paid a visit for a month to the Institute of Theoretical Physics in Helsinki in Finland. And the director, as soon as I got there, the director of the institute, Vinaya Magalkar, told me that there was an experimental physicist, Olli Liljesmaa, who was trying to cool liquid helium, or more precisely use, I'm sorry, that's wrong. He was trying to cool liquid helium to lower temperatures than anyone had previously achieved. And the way he was trying to do this was to put the helium in contact with a metal and cool the metal. Now, the problem with that is that it's really rather difficult to get heat, or actually in this case, the coolness out of the metal and into the helium. There is what is called a thermal boundary resistance, or technically a Kapitsa resistance, between the metal and liquid helium. And there was a student in Vinay Abagarkar's group, Mativorio, who was trying to look at this problem, and Vinay suggested to me that I should try to collaborate with this student. So the student was particularly interested in the special behavior of the thermal boundary conductance, the Kapitsa conductance, between helium-3, the lighter isotope of helium, and a substance called cerium magnesium nitrate, a particular salt, which in those days used to be a favorite for magnetic cooling. So again, people were trying to cool the magnetic salt and then transfer the coolth to the helium-3. And this seemed to have very peculiar properties. For all other known substances, if they were put in contact with a metal or with this salt, or indeed with just about anything else, the efficiency of thermal transfer across the boundary decreased strongly as you lowered the temperature. In other words, the thermal conductance went down, the resistance went zooming up. And this was a major problem, really. But in the case of this particular salt, it was actually going down, quite contrary to what everything else was doing. Now, the first thing that Matti showed me when I started to talk to him about this problem was a recent review article on this thermal resistance problem. And this problem was nearly up to date. It hadn't quite got up to the most recent experiments, but it was pretty much up to date. And it listed all the theories and all the experiments, and the theories and the experiments seemed by and large to be in pretty good agreement. And there were about 90 of these papers listed. And the first thing I said to Matti is, we are not going to read those 90 papers. Why not? Because they're clearly wrong, at least as regards our particular problem, that is the resistance between helium-3 and cerium magnesium nitrate. Because all the theory papers said, just as all the other experimental papers said, was that the thermal resistance should zoom up as I went to lower temperatures. And in this particular case, it was doing precisely the opposite. It was zooming down. So it's entirely clear that these 90 papers were totally irrelevant. And so I said, let's forget about these. Let's start about thinking about the problem from scratch without worrying about what people have done so far. And we took an idea, which is not entirely original to us. The experimentalist John Wheatley had at least qualitatively proposed it. We took the idea that the whole mechanism of transfer in this particular case was totally different from what it was in all the other cases, and in fact had to do with the spins in the materials. And out of this, we were eventually able to make a reasonable quantitative theory. So that was certainly a case where it was sensible not to look at the existing literature. Now I want to go back a little in time to an episode which happened when I just after I'd finished my my doctorate at Oxford, I went as a postdoc to the University of Illinois, where I'm now, to work with David Pines. And at that time, John Wheatley, in the basement at the University of Illinois, was cooling, again, liquid helium-3, one of my favorite subjects. He's cooling liquid helium-3 to very low temperatures because people had predicted that it would behave similarly, it might behave similarly to a superconductor. In other words, it would form what we call Cooper pairs and become superfluid. But what John was actually doing was to measure the spin diffusion coefficient, a particular property of the liquid. And no one knew what this particular coefficient was going to do if indeed helium-3 did become superfluid. So one day John Bardeen and Leo Kadanoff, two of the leading theorists at the University of Illinois, came into my office and said, look, John doesn't know what he's looking for, so why don't you try to predict what's going to happen if liquid helium-3 does indeed go superfluid. So I started out thinking about this. And in those days, there were two major theories which were in some sense dominating condensed matter physics, or at least the low temperature part of condensed matter physics. One of them, which I didn't actually know much about when I arrived at Illinois, was precisely the theory of Bardeen, Cooper and Schrieffer, three people at Illinois, of superconductivity. That was, by the time I got to Illinois, that was about 7 or 8 years old. The other was a theory which had been evolved by the Russian theorist Lev Landau about the properties of normal, that is non-superfluid helium-3, which tried to take into account the fact that helium-3 was not really like a gas of non-interacting atoms. The atoms were really interacting pretty strongly. So you had these two theories, and they didn't seem to have made any contact with one another, at least not much. I did take a brief look at the literature, and I found that there was one paper, again by a couple of Russians, who had worked out how you'd put these two theories together at 0 temperature. It was pretty boring. It just multiplied everything by a constant, or made it 0. Nothing at all interesting. But John Wheatley was not going to be working at 0 temperature. He was going to be working at much higher temperatures. So I felt I had to try to generalize the idea to finite temperature. And when I did, I was really expecting that the result would also be pretty boring at finite temperatures, but nevertheless, I felt I had to do it. So I started off doing a very complicated calculation using some theoretical technique which we call Green's functions. You don't really need to know what that is, but it's a very high-powered theoretical technique which was very popular in those days. We graduate students in Oxford practically lived on that. And so I played around with this and tried to apply it to the problem I was interested in. And at the end of the day, when I finally managed to get out a sort of concrete conclusion, I found out, wait a minute, it really isn't so boring at all. What it's going to do is not just multiply everything by some boring constant, it's going to change the actual shape of the dependence of various quantities on temperature. Then I thought to myself, well, look, this really isn't very convincing. I've been through all this theoretical rigmarole, which most people don't understand. No one is going to really believe it if this is all I do. So I decided to try to find a much more intuitive way of looking at that problem. And eventually I came up with a technique. For what it's worth, if anyone knows about it, it's called the generalized molecular field technique. But anyway, it's a very much simpler phenomenological way of looking at the problem and deriving all the results I did. Now, the reason I was motivated to do that was that I was very excited by this result which I got by these high-powered theoretical methods. And I thought, wow, this is completely new. No one has ever found this before. That's why I have to try and do a much simpler theory of what's going on. Well, all well and good. I wrote up this theory, both the high-powered theoretical stuff and also the phenomenological theory. I wrote a couple of papers at a big international conference. One of the leading speakers happened to mention this work of mine, which made me very proud. Because I should say, in those days, I'd just come off my PhD. So very unconfident and hesitant postdoc. And so this really gave me an enormous boost to have done this and to feel that I was really, as it were, the first person in the world to have done this. Well, actually, it turns out I wasn't. A few years later, I discovered that one of my results had been anticipated in a paper which had appeared a couple of years earlier. And literally 30 years later, I eventually discovered that if you actually read one of the Russian papers sufficiently carefully, you could actually extract that result. They'd also done this high-powered theoretical technique, and if you really worked at it, you could extract my result from it. So it's very messy and complicated, and I actually thought my phenomenological method was much nicer and much more elegant and so forth. But I often wonder what would have happened had I actually realized at the time I did this, had some malevolent person told me that this was not a new result, that it had been done by someone else. I think I would not have been half as excited. I would not have had the adrenaline rush, and I wouldn't have done the rest of the elegant phenomenological work which I ended up doing. You see how I'm doing for time. Yeah, okay, good. Okay, the next thing I'd like to talk about, which was actually in some sense perhaps a little more, I don't know, more spectacular, was the work I did in connection with some experiments which were done at Cornell University in the US in the early 70s, again on my favorite system, liquid helium-3. The Cornell group were doing standard nuclear magnetic resonance experiment on liquid helium-3. Now, nuclear magnetic resonance is a very well-known technique. It's been around for many decades. There are large books which are written on the subject, including, for example, a sort of standard text which had been written by the late Charlie Slifter, my colleague, when I'd been a postdoc at Illinois. And they found, the Cornell group found something very odd. They found out that the so-called resonance frequency, the frequency of the radio frequency field at which it was strongly absorbed, was behaving perfectly normally and understandably above about 3 milledegrees, 3,000th of a degree absolute. But then below that temperature, it suddenly started zooming up away from the good old standard value. It went on and up, and then suddenly, at a second temperature, about 2 milledegrees, it dropped back to the original value and stayed there. That was really weird. And so I thought to myself, well, look, this doesn't seem like anything which is currently known in nuclear magnetic resonance. Therefore, it cannot be something which is well accounted for by the existing literature, including these large textbooks. I did not know any of the standard literature at that point. And again, I decided, well, it's better not to know. It's better to just ignore what all the textbooks say and just go ahead, bash it out and see what I can derive from first principles. Actually, just as a matter of interest, my motivation was a peculiar one. I had, just at that point in time, I was by that time at the University of Sussex as a junior faculty member. And just at that time, I'd really got a bit bored with low temperature physics, and I'd decided to devote myself to something I found very interesting, which was the foundations of quantum mechanics. But this result seemed to me so weird that I seriously wondered whether it wasn't the first evidence for the fact that under the very extreme conditions of the experiment, very low temperatures, very dense system, no one had ever explored this regime before, maybe under those very extreme conditions, quantum mechanics might actually be breaking down. So I really took this idea seriously. And what I originally set out to do, in fact, was to construct an explicit proof that if standard quantum mechanics was working and standard statistical mechanics was working, things we all believe, then this experiment just could not happen. As it were, the data had to be wrong. Well, of course, had that actually been the case, you'd have heard about it. So that turned out not to be the case. And in the end, I did manage to get a reasonable understanding of what was going on, based on an idea which I thought was sort of rather interesting. The technical name for the idea is spontaneously broken spin-orbit symmetry, but in view of the limited time, I think perhaps I better not try to go into exactly what that was. But anyway, it had that idea, at least at prima facie, had really very, very little to do with the standard ideas of nuclear magnetic resonance, which are in all the textbooks and so forth. It was something really rather different. Now, I always say that I think the only reason I was able to do that work at the University of Sussex, and this is, we're talking now about the early 70s, was that I knew what I needed to know. What I needed to know was the experimental properties of liquid helium-3, which I actually knew quite a lot about, and at least some idea of existing theoretical ideas about liquid helium-3. But I also did not know what I needed not to know. I did not know the standard theory of nuclear magnetic resonance. And the reason I say that is that as I was doing this work, lots and lots of other people also tried to look at the problem. Almost without exception, they were looking at it in the light of this standard textbook approach. And they really, in the end, pretty much got nowhere with that. And so really, that's another case then in which really it was helpful not to know the existing literature. The final example I'll try to give comes from a somewhat later period in my career when I was pretty much settled in at the University of Sussex. And by that time, I had eventually managed to get back. I'd done quite a bit of work on what we now call superfluid helium-3, and I eventually got back to what had been my original ambition, namely to look at the foundations of quantum mechanics. And I became very, very fascinated by the so-called quantum measurement problem. And very roughly speaking, that goes something like this. If I'm talking about a microscopic object, like say an electron or a neutron or whatever, then it seems that in some way, if I don't look at it, then it may be doing two things at the same time. A very standard example of this is if I have a so-called 𝐤𝐬𝐬𝐷 experiment in which let's say a neutron, or an electron for that matter, has the possibility of going through one of two slits in an otherwise opaque screen, then it somehow looks as if I don't look at the electron, then it will somehow manage to go through both slits, or at least not to go definitely through one or the other. Now, how you actually describe that is a matter of taste. I mean, some people say it goes through both slits, some people say it goes through neither slits, some people say the question is not well defined, but the one thing that you can't say is that each given electron which goes through this apparatus definitely goes through one slit or definitely goes through the other. That's one thing that doesn't seem to work at all. But now, remember that ordinary, everyday level, or macroscopic as the technical term goes, everyday level bodies, like say cats or Geiger counters or whatever, are actually made up of atoms and electrons and so forth. And therefore, you'd expect that if quantum mechanics describes the behavior of the individual electrons and leads to these funny consequences, then in some way quantum mechanics ought also to describe the behavior of the counters and the cats and so forth. And in principle, at least, it ought to lead to the same kind of bizarre consequences. And some of you may know, this is actually encapsulated in a very famous thought experiment which Erwin Schrödinger, one of the founders of quantum mechanics, proposed in 1935. And he pointed out that if you really believe that quantum mechanics is the whole story and applied not just to atoms and electrons, but to small molecules, to large molecules, to bits of experimental equipment, to cats, etc., then you could, in principle, rig up an experiment in which you had a cat inside a closed box. And until you took the lid off the box and looked at it, that cat was neither dead nor alive, but in some kind of curious combination of being both at the same time. That's usually called the Schrödinger's cat experiment or paradox. And yet, no one seriously doubts that if you take the lid off the box and look at any particular cat, she will be either alive or dead. Not one, not for both. It'll be either or, not both and, right? So that's the, in a nutshell, the basic quantum measurement paradox. But now, lots of people had sort of discussed the question, well, can we actually do, as it were, do this experiment? Can we actually see if this is right or not at the level of cats? And almost without exception, they've come to the conclusion that the answer is no. And the reason the answer is no is a rather technical one, but I'll just try to give the essence. It's basically because you only get peculiar consequences out of this very bizarre description in which the cat is neither alive nor dead, if you are allowed to, as it were, recombine these states with the appropriate phase relation between them. And there's lots and lots of literature which said that, well, yes, but the moment the cat is in contact with any kind of outside world, like the electronics or the gun or the cyanide which is going to kill her, or just the air in the room, that'll do, then this will mess up the phase relationship between these two states, and therefore the bizarre description will actually only have the same experimental consequences as the common sense one, which says that the cat is either alive or dead, and you just didn't know which until you took the lid off the box. So I had vaguely wondered whether that was right, but all the literature in the so-called quantum foundations area seemed to be saying, yeah, that's what's going to happen. No point ever in trying to do that kind of experiment. It just isn't going to give any information. But sometime in the late 70s, a young experimentalist, Terry Clark was his name, came to the University of Sussex, and he was a great expert on a kind of electronic device. This is one thing actually which might be vaguely relevant to the subject of this conference. It's a Josephson device, what in those days was called an RF squid, but nowadays it's more glamorously called a flux qubit. And he had the idea, and he's very keen on the idea, that this RF squid or flux qubit was really just like a huge atom, and it behaved, it was going to behave in exactly the same way as a huge atom, and everything you could say about the atom, you could say about the squid. And if that were really true, of course, then, well, you might not be able to do an experiment with your cats, but you could do an experiment with squids, and you would expect them to see this bizarre behavior. Well, my immediate reaction was, no, look, there's 40 years worth or more of quantum measurement literature which says that this can't happen for the reason I mentioned, that the environment, all the things that are not the cat, or the squid, the air in the room, etc., is going to spoil this idea completely. But Terry didn't know about this. He had not read the quantum measurement literature, and he did not intend to read the quantum literature. He intended to go on doing his experiments and try to show that indeed this would happen. Well, I was really very doubtful, but Terry was very persistent, and he had one or two theoretical collaborators who were also addicted to the same idea. So I thought, well, I should try to pin this down a little more precisely. I should see how far these general ideas which have been discussed in the quantum measurement literature would apply to the special case of a RF squid, or as we know, so a flux qubit. And so I went away, and I actually did several years worth of theoretical work on this. And eventually I came to the conclusion. First of all, I really didn't think that the experiments Terry was doing were going to work. I still don't think they worked. I still don't think that they showed what he and maybe some of his collaborators thought they'd showed. I think it's a much simpler common sense explanation of what was going on there, but that's a different story. But what was more interesting was that I came to the conclusion that if you really worked hard enough and tried to cut down the effects of the outside world in various ways, there are ways you can try to do this experimentally, then if you worked hard enough, you might eventually be able to get to the point where indeed the squid was behaving pretty much like a large atom, and it was showing the same effects as the cat in Schrödinger's thought experiment. Again, that got lots and lots of flack from the professional quantum measurement people. We stuck at it, and very luckily the experimental community was much more open-minded about this, and they really worked hard on trying to cool their squids or flux qubits down to lower temperatures and to isolate them better from the outside world, and so on and so forth. And sure enough, about the year 2000, they did actually start to see precisely the Schrödinger's cat-like kinds of behavior that that quantum mechanics left to itself would predict. And over the 20 years since then, this has become more or less just completely common sense, common knowledge in the field. So you now find, ironically, young experimental physicists with writing papers about these systems, which have words in the title like artificial atom and so forth, without any realization of how controversial this was around the 1980s and 90s. But that was another spectacular case, I think, in which in this case, not my ignorance of the literature, but Terry's ignorance of the literature really caused something to happen, which otherwise might well not have happened. So I think we're probably getting fairly close to my time, yes. Okay, so, well, to sum up, when is it and isn't it a good thing to know the existing literature? Well, first of all, I think it's almost always wise to know at least the basics of the experimental literature, to know what is the experimental data, the basic experimental data in your subject. Otherwise, you really risk getting egg on your face if you predict something which has nothing to do with the experiments. On the other hand, you have to know when to discard the existing experiments as irrelevant, as, for example, we did when we were thinking about the thermal boundary resistance between helium-3 and CMN. If the phenomenon you're looking at is so obviously different from what is in the rest of the experimental literature, then you can probably ignore it. So that's what we did with that thermal boundary problem. It's what I did with the helium-3 nuclear magnetic resonance, and so forth. What about theory? When should you spend a lot of time learning up existing theory? Well, in some cases, the theory is obviously wrong. That was the case, for example, that Einstein sort of felt in his bones the ether theory was obviously completely wrong. It was nonsense on, as it were, a priori grounds, and therefore he didn't really have to learn about all the theoretical work which had been done using the ether theory. So that was a case where it did pay off not to know the existing theoretical literature. On the other hand, for example, in the case of, well, this is an experiment rather than theory, but in the case of Galileo, he really got egg on his face by not knowing the basic experimental facts. But now the much more interesting case, what if the theory is maybe right? Is it necessarily a good thing to learn up all the theory before you start thinking about the subject? I don't claim no, actually it isn't. As I say, had I actually known, or had some malevolent person told me at the time I was doing the work that I did as a young postdoc, on putting together the Landau theory and the so-called BCS theory of superconductivity, had I known that that already existed, I've got nothing like the adrenaline rush that I got. I wouldn't have been motivated to go on and try to reformulate what I'd found in a more phenomenological and, I would claim, a more elegant way that had been done at the time. So the feeling of that adrenaline rush really is quite important. I used to be, this is a slight digression, but it's an analogy, I think. In my younger days, many years ago now, I used to be a quite keen rock climber. And in the rock climbing community, we used to discuss whether it was a good idea, if you're going away to a rock face in North Wales or Scotland or whatever, to do a climb on a rock face where you've not been before, should you read up on it? After all, there were in those days and still are, lots of little handbooks which tell you about these various rock faces, and they tell you which climbs have been done and how hard they are, and so on and so forth. Should you read those before you go there? And most of us came to the conclusion, most of us in the rock climbing community came to the conclusion, no, it's better just to go and do the climb as if no one had ever done it before. And so if you do that, you'll get an enormous feeling of satisfaction. And then, of course, if you come back and a couple of years later, you find out that this is a well-known climb, it's got a name, it's been graded for difficulty, etc., etc. Well, who cares, really? Didn't spoil the sense of excitement you felt when you first did it. Of course, the one caution, of course, if you do indeed think you've discovered something genuinely novel, then before you rush out and publish it or try to publish it, you better just do a bit of checking to find out, as indeed I did. I did not, in fact, find the anticipations because they were rather obscure and difficult to find. But you do need to find the anticipations, otherwise, again, you risk getting a lot of ego on your face. Well, as I say, this is one of the things. I spent a whole hour basically on telling you one of the things, bits of advice I usually give when people, young students and so forth, ask me for general advice about how to embark on a scientific career. What about some of the other things? Well, one of the other things is, perhaps more important really, sort of logically prior to this, is whatever else you do, follow your own curiosity. And don't worry if if you're asking a particular question and it really intrigues and worries you and fascinates you, don't worry if everyone around you says, oh, that's a stupid question. Everyone knows the answer to that. Think, for example, of Einstein. Again, different case, but different topic. But think about Einstein and gravity. For 250 years before Einstein, people had known as an experimental fact that all bodies, irrespective of their shape, their size, their composition, ... they fall in vacuum under the Earth's gravitational field at the same rate. No one had wondered why. And I'm sure when Einstein started asking why, I'm sure all his contemporaries tapped their heads and said, oh, that's a stupid question. Everyone knows that. They just do. And yet, by thinking about that simple question and worrying it to death, Einstein came up with the theory of general relativity, which is perhaps the most elegant and beautiful part of the whole of modern physics. The third thing is never think any piece of research has been wasted. If you've done a piece of research and you've done it honestly and conscientiously, even if it didn't turn out the way you hoped, even if it turned out, say, the experiments on which you were basing it were wrong, whatever, don't worry. Just make sure you write it up. Write it up carefully, put it away in a drawer, and I will bet that 10 or 15 years down the road, it'll come back and help you out. This happened to me, actually. I didn't, in fact, mention it at this point in my talk, but when I was thinking about the the possible theoretical description of the nuclear magnetic resonance in what we now call superfluid helium-3, I was helped out. In fact, it was absolutely vital that I had done an earlier piece of work about 8 years earlier on a little problem in superconductivity, which the moment I'd addressed it, more or less disappeared. I'd been doing it on the basis of a certain experiment, and the moment I'd done the theory, it turned out the experiment was wrong. So it looked as if it had absolutely no use, no application. And yet it was precisely that little piece of work which came back and helped me in an emergency with superfluid helium-3. And finally, one thing I would really like to say to any young scientists who are listening to this talk: if you're going into a career in academia, whether we're talking about high school or university or whatever, but anywhere where part of your job is teaching, then for goodness sake, take your teaching at least as seriously as you take your research, even if not more so. I would claim that I actually learned at least as much, and probably more, over my career from my teaching activities as I have from my explicitly research activities. So if you focus on your teaching and do it conscientiously, it's not just going to be good for your students, it's going to be good for you. And that's basically what I'd like to say. Thank you.
Thank you, Prof. Leggett. That's definitely very interesting. Last bit of your advice was definitely useful to our young lecturers. We have time for a few questions. There is one from Prof. Mujahid from University Pertahanan. Prof. Mujahid, are you there, Dr. Mujahid?
Thank you, Prof. Very inspiring topic and discussion, Prof. I have one question here. Well, in the advancement of technology, the subatomic world of quantum mechanics is almost possible. And my question is, can human teleportation be possible, Prof? Thank you, Prof.
Well, okay, yes, one does see the word teleportation used quite a lot these days in connection with certain experiments done in connection with quantum mechanics. What is actually meant by teleportation is really pretty far from what you think of in the context of Star Wars and so forth. It basically means conveying information about an unknown state to a distant sender without, as it were, communicating physically and directly, with a distant recipient, I should say, without the sender and recipient communicating directly. One can imagine that eventually, right now, it's at the level, this so-called teleportation is at the level of single particles, mostly single photons. And one can imagine that it will be extended to single electrons, eventually to perhaps single atoms, eventually single molecules, and so forth, ... I actually think it's going to be many thousands of years, perhaps even tens of thousands of years, before people get anywhere near being able to teleport a complete human being. In fact, I would suspect, more seriously, there may actually be really a priori considerations which forbid that. For example, it may be that it's essential to the whole notion of a human being, or indeed an animal, that it is not in thermal equilibrium and has a very delicate relationship with its environment. And this may, perhaps in the end, turn out to just totally prevent the possibility of teleportation. But in any case, even if it is possible, it's many, many tens of thousands of years ahead, I would say.
And that's a shame, because we thought of beaming you here for the next conference.
Yeah, I'm afraid that probably won't work.
So can we have another question, please?
Tony, I like your analogy of rock climbers as yourself not knowing the dangers ahead, so as not to discourage your the zing that you get. But let's say we divide your definition of a young researcher to two categories. One who has obtained a doctorate and one who is embarking on the doctorate. Then isn't there the juxtaposition of literature review quite evident? Quite critical on the two stages?
Well, okay. I mean, that of course brings up a huge topic, which I actually have rather strong feelings about, which is the degree of pressure which most young scientists, certainly most young physicists, are under these days, in the sense that they've got to, if they're doing a doctorate, they have to complete the doctorate perhaps within 3 or 4 years. If they're postdocs, they have to have published half a dozen papers within 3 years in order to qualify for a faculty position, etc., etc. So what this means is, of course, that the kinds of problem that you're likely to focus on, or I mean, if you're a doctoral student, the kinds of problem that your doctoral advisor is likely to suggest to you are precisely those problems which are likely to be soluble within 3 years or whatever. Now, almost by definition, those are going to be the problems which can be solved with the help of the existing literature. So yes, I mean, you will find that most problems on which people tend to do their PhDs do require people to go and look at the existing literature. But in some sense, almost by definition, those are not the exciting problems. And you're very lucky if you find, as for example, Brian Josephson did many years ago, if you manage to find yourself a problem where the existing literature won't help you at all, and you just think about it yourself from scratch. But Josephson is a very unusual case, I should say.
Right, Prof. Leggett, sorry. Is there anybody else?
The same thing. That's one of the, as you said, the published literature is quite vast these days. To find a problem itself is a problem.
Yeah.
So I wish time was turned back.
Yes.
To the early days.
You know, I'd have to say, I mean, this is sort of slightly off the topic, but since the question of time constraints was at least implicitly raised, I really think that I was incredibly lucky myself in being able to work at the University of Sussex during the early 70s under essentially no pressure to publish. I had got what is essentially a permanent position at the University of Sussex. I mean, it was only a lecturer's position, but it was essentially tenured and permanent. I really didn't have to worry about publishing X number of papers in order to get tenure or promotion or anything else that people have to worry about these days. And I think that was absolutely fundamental in allowing me to do the work I was able to do, for example, on superfluid helium-3. And I really feel very sad that I suspect most young scientists these days don't really ever have that experience. They're always under some kind of pressure to, publish 6 papers in Nature and Science in order to, during your doctorate, in order to get a decent postdoctoral position, publish 10 papers in Proceedings of the National Academy in order to get a tenured faculty position, ... It's really hard. It's really nonsense, I think, but frankly, I don't know what to do about it.
Right, Prof. Leggett. So that's it's about time now, but one last question for me. Don't you ever get bored with what you're doing over so many years?
Not really, I think. There are always new questions coming up.
How do you continuously motivate yourself?
Sorry, well, how am I motivated? Well,
how do you motivate yourself over the many years?
Well, I mean, I'm not a great believer in the idea that there's so-called fundamental physics and non-fundamental physics, and that I mean this belief is usually held by people who are specialists in particle physics or cosmology. Basically, according to that point of view, it's elementary particle physics and cosmology, which is basic physics, and everything else is just a consequence of that. Well, I'm saying it's just or only a consequence of that, I think is grossly misleading. When, as Phil Anderson, the late Phil Anderson, used to emphasize repeatedly, when large numbers of atoms get together, they can really show behavior which is totally qualitatively different from what any of the atoms individually could do. So I find it really fascinating to see what these collections of atoms together can do, and they can do all sorts of fascinating things. They can lead to superconductivity, they can lead to superfluidity, and they can even lead to, of course, practical inventions like the laser, which again is not something you get at the single particle level at all. So I'm not in any sense bored or regretful that my field of expertise is condensed matter physics. I'll go on doing it, I think, to my dying day and love it.
Right. Prof. Leggett, I think the organizer will allow me one last dumb question. As a Nobel laureate, you still get nagged by the wife? You still have to do chores? Do
I still get?
Do you get nagged by the wife, or do you still have to do chores at home, or do you?
Oh yes, yes. Definitely.
Even as a Nobel laureate.
I'm afraid so. Yes, it doesn't get you out of that.
Right. So with that, thanks, Prof. I mean, it's been a very delightful morning for us here. We really look forward to hearing from you again. Hopefully, you will be physically next time, but otherwise, we can have more and more of these sessions. So, thanks, and I pass it back to the chairman.